right, let's start. They are going to join us. Bob Youngs is going to present Chiou Young's GMPEs model, latest and greatest, based on 2008. Is that what you said?
Update to
Update. Oh, I see. Okay, very good. Thank you very much, Bob.
Okay, good afternoon, everyone. So I will be presenting what Brian and I have done to update our model. Since Brian did all the work, I do the presentation.
Same thing, yeah.
Well, you're going to have to work that out on your team. So the data we use for our analysis, we are using the PRNGA2 database. We removed earthquakes flagged as not shallow crustal events, basically the same kinds of events we removed in the 2008 model. We used the same acceptance criteria for site classification as we did in 2008, which means we are including dam abutments in our analysis. One couple of changes from that for our preliminary analysis. We've only used data with earthquakes with at least 5 recordings per earthquake, which is not what we did before. And for this first pass through, we've only used data defined as C1 based on the 40-kilometer distance increment. We need to look at, we haven't had a chance to look at the aftershock scaling criteria. So we started off with this events beyond that. We know there wouldn't be any aftershock issues. So we expect it to be gone definitely by 40 kilometers. One of the things that has been mentioned earlier, that in the database, there are a lot of missing Z1.0 basin depth parameters in many sites because they did not have data to estimate the basin depth. So as we did in 2008, we've estimated that based on correlations between VS30 and Z1.0. And the work, we have a lot of data now from Japan, and when we do the work, we see a different correlation between basin depth in California and VS30 than in Japan. And which is not surprising given that we see lots of other differences in effects of the sites in between the two regions. So we were using these to populate the missing Z1.0 values in the flat file for our use. In terms of differences, the basic model is pretty much unchanged in terms of its form. For the magnitude scaling at large distances from the source, we're using the 2008 form, which is basically consists of 2 linear trends at high magnitudes. Let's see, wake up here. So at large magnitudes, we have a linear slope with magnitude scaling at a particular period, and at low magnitudes, we have another linear slope, and then we have a smooth transition in between, which is controlled by 2 parameters. Cn basically determines the width of it, and Cm determines the center point of that. We found that worked really well in 2008 in looking at smaller magnitude data, and was reconfirmed in Brian's paper in 2010 when we definitely looked at a large amount of small magnitude data. So we are continuing to use this form, and that we think this form works well over magnitudes from 3 to 8. And it provides a smooth transition. It's doing the same types of things that the multilinear breakpoint model of Ken, who just talked about, is doing. Scaling with top of rupture, we examined the scaling compared to the 2008 model, depth of top of rupture. I also would like to echo what Ken and Joseph have found, that hypercenter depth actually works better than Z top of rupture. But we chose to use top of rupture because of one of us is a practicing hazard analyst. So. We do find that the depth to top of rupture term scaling is stronger than it was in 2008 at high frequency, and is somewhat weaker at lower frequency. And after hearing Ken and Joseph talk about the effect of dip at small magnitudes, we looked at it, and we found, indeed, there is a very strong effect of dip for smaller magnitude earthquakes. And the problem we see is that dip and depth and mechanism are probably all correlated in some fashion, and we need to work out how that process is working. So we have right now to put in a dip dependence for small magnitudes and kept the depth dependence, kept the mechanism basic effect the same at large magnitudes as we had before. But we need to work out how all those things work together. And this is a plot that's showing the event terms. These are computed using our old depth scaling terms from 2008, and we can see that there's a trend in within the event-to-event or the event terms with depth that's stronger than what we had before at high frequency and weaker than we had before at low frequency. So the depth scaling terms needed to change in terms of their amplitude. And here's the effect of dip, which shows up strongly in the trends of residuals for the model without. If you just put depth in, you still see this very strong effect with dip at the smaller magnitude range. So our basic scaling model in terms of magnitude size is very similar to before, except we've added this term for smaller magnitudes below magnitude 6, where we see a dip effect. The distance scaling is unchanged from, in terms of form from 2008. We basically have two terms that deal with geometric spreading, and then an anelastic attenuation or Q term that deals with anelastic attenuation and scattering, which we've stolen the term that Ken used years ago, which is gamma, to represent this term. So basically we have a near field geometric spreading, which is R plus C or R plus H. So it's somewhat different than the other. We don't do the R squared plus the square root of R squared plus H squared. We have a magnitude dependent H term, which is constructed basically to prevent oversaturation. Then we have a change in geometric spreading from basically a term that would be 1 over R-ish or body wave type in close to a more LG wave or surface wave type spreading, which we fix at a half at larger distance beyond 50 kilometers with a smooth transition in between. That's all unchanged. And then at the large distances, we have the anelastic gamma term to compensate, to show the roll-off of distance at very large distances. And this is all illustrated with the data from Parkfield right here on this example slide. In terms of the near source saturation term, the H term, it's constructed as a smooth transition that represented the old, say, Sadiq form or others form. I think actually Etcheva actually probably first came up with it. In terms of a term that would, so that the slope of this with magnitude interacts with the magnitude scaling term and the near source distance scaling term to prevent oversaturation. So what's shown here is the model we developed in 2008, and then the points are estimates of that H term at 2 periods from the newer earthquakes, and we felt that they were consistent with the old model. So right now we've left the old, basically H term as it was defined in 2008. We have looked extensively at the regionalization of the gamma term. And we've done this following the approach that we used in 2008. So we've gone through and analyzed individual earthquakes in the database. We've done this analysis with a truncated regression, which allows for data truncation horizontally at specific ground motion levels. The difference between the analysis now and in 2008 is now we have included the basin term in this estimation. And we've used earthquakes to do this with a minimum of 5 recordings per that distance is less than 100 kilometers and 5 recordings at distances greater than 100 so that we can get a reasonable slope trend. And then we've examined the effect of different truncation points on those estimates of gamma. Here's an example from San Simeon earthquake. These are 8 periods from PGA out to 2 seconds. So PGA 0.05, 0.1, 0.2, 0.3, 0.5, 1, and 2 seconds, showing the effect of estimation of fitting the functional form to this model. So everything is fixed in this functional form, except the amplitude of the curve itself and the gamma term at large distances. And then we look at the effect of truncating at different points on the estimates of gamma. And for this earthquake, you can see truncating at different points does not produce a significant difference in the change in gamma. And basically, the truncated regression model is a model that says that at some point, the lower part of the distribution is missing. So you put that into the likelihood function to estimate the regression term, allowing for the fact that data is missing at the low amplitudes. So this is an example for San Simeon. So I went through the entire NGA West 2 database event by event to do this assessment for those events that had at least 5 recordings less than 100 and 5 and greater than 100. And this is a plot of the estimates of gamma as a function of magnitude for California. The red circles and symbols are for Southern California, and the blue circles are Northern California. And when this had been done originally back in the spring, we were first looking at this, we were seeing a difference between Northern and Southern California. But now when we put in the basin term and the fact that many of the data points in Southern California are on deep basins, the difference between Southern and Northern California has disappeared. And we don't see a statistically difference in gamma across California, which is good news. So we hopefully don't have to regionalize California. And so the model that we've come up, so we fit this with a magnitude-dependent model. So we have a magnitude-dependent gamma term shown by this the dashed line here, which is also period-dependent. And then we use this model in our regression. We fix the gamma term, and then we use data only out to 70 kilometers for the regression at this point, anyway. And then the far field, but we put the gamma term in that regression as a fixed parameter. So it's dealing with the correct far field fall off. And as we saw in 2008, we were able to extend that model out to large distances and look at residuals, and it was working well out to large distances. So we feel that this approach is working well in terms of being able to extend the model beyond the point where we're ending the regression. Now, gamma for other regions. So this is the analysis we've done with the other data in the NGA database, NGA2 database for larger magnitudes. The black line is, again, the California model. In here, we have the green symbols are Japan. And as Ken and others have mentioned, Japan is falling off, has a larger gamma, largely more negative gamma term, so greater inelastic attenuation or scattering effects. And Italy there's only a couple of earthquakes we can do this with right now, and they are showing similar effects to Japan. So we would, as Ken and others have indicated, we would lump Italy and Japan into the same category for inelastic attenuation. Looking at New Zealand and Turkey and Taiwan, they're similar from these data points to California, so we would consider them California-like. And as has been mentioned, the blue ones here are the Wenshan aftershocks, and the Wenshan main shock is up here, which is a very well-constrained. These are 90% confidence intervals on the estimate of gamma at each point. Wenshan has a lot of data, it's very well-constrained, and it definitely has much lower gamma than California. So now at this point, what we've done is we've only included in our initial model, we're basically trying to focus on a model that's good for California. So we've done our first pass through, and the model that's in the preliminary model is based on California or California-like sites, earthquakes. We've not included Japan. We've not included Wenshan. We need to analyze beyond just the effect of difference in gamma. We are hearing definitely, we see when we did our initial analysis differences in VS30 scaling in Japan and perhaps in Japan. So we need to look at that in more detail before we bring that stuff in. So the basic conclusions are, as I said, inclusion of the depth term to ZEEP 1.0 produced no difference between Northern and Southern California. We can include New Zealand, Taiwan, and Turkey as similar to California, Japan and Italy in one group, China in another group. The site amplification model is unchanged from 2008. We, in 2008, developed an empirically based linear and nonlinear VS30 scaling. So we did not use the Walling et al. Method or Chiou and Stewart. We looked at those methods, and we derived one from the data, and which came out to be fairly similar. So we're still basing it on our estimate of the data. And for this analysis, we have not changed it. And so I will be showing you residuals from the new data set compared to a model which is using the 2008 soil parameters. And also, we used an empirically based Z1.0 scaling parameter which has this form, and we have not changed that again from 2008. So the model that is that we're presenting now is basically the 2008 site amplification model, and the residuals I'll show you are with respect to a model based on that, using those amplification terms. So some residual plots. This is basically plots of magnitude scaling, event terms above magnitude for PGA or 100 hertz frequency. You can see that the model is fairly flat. There's a tendency to perhaps overpredict. Again, like everyone else, we're not allowing for oversaturation. And you have the Chiou residual down here. 0.2 seconds and 1 second. These lines on here are locally weighted least squares fit to the residuals. And you can see they're fluctuating around 0. Here are the plots of the intra-event residuals versus magnitude, from magnitude 3 up to 7.6. Again, very flat, so that the magnitude scaling is working within the event terms all the way out. I mean, within the earthquakes all the way across the magnitude range. This is our distance scaling term. Again, we're regressing out to 70 kilometers. With the terms fixed, using all fixed based on the 2008 model. The only change is we've now imposed a new update to the gamma model, which has some impact at the edges of this. And again, the terms are well behaved. In terms of the Z1.0, this is the model, as I said, was fixed based on the 2008, and it works well for the shallower depths, but we are tending to overpredict at the deeper depths, and that is because there's been some significant changes in the estimates of Z1.0 for a number of the sites from 2001 to 2002. So we'll need to fix that term a little bit for the deeper basins. And this is the residuals against VS30, and this is, again, this is a residuals that were developed using the 2008 soil amplification terms, and we see that it's working very well in predicting the new data set. So this is a comparison of the model. The solid curves are the 2012 update. The days curves of the 2008 model. This is PGA, and at large magnitudes they're very close, and at smaller magnitudes we are getting, like all the other investigators, when they include the smaller magnitudes, we're getting lower estimates than our 2008 model. Brian has done a comparison also with Chiou et al. 2010, and the new model is very similar in terms of smaller magnitude scaling to the 2010 model. This is 0.2 seconds. Now, again, the same trends, except that now we're getting a little bit higher 0.2 second motions than we had before. And this is 1 second. And again, we're getting a little bit higher 1 second motions than we had before. This is basically the shape of the magnitude scaling as a function of at different distances from 10 to 200 kilometers. And the basic shape of our form from 2012 is the solid curves, and the 2008 model is the dash curves. So we were, again, in 2008, we were over-predicting at the lower magnitudes, and now the trend is fitting those data better. 0.2 seconds, 1 second. So what's left to do? Just a little bit. So we need to resolve the model for the depth mechanism interaction. We need to figure out a way to account for any correlations that would affect those terms. We need to incorporate data from other regions with different values of gamma. And to do that, we're going to need to look at some more smaller moderate magnitude data sets from those other regions to help constrain the gamma model. And then to check for differences in VS30 scaling. We need to update the Z1.0 scaling. Right now, we have not modified the hanging wall model from what we had in 2008. Our formulation did generally what Jennifer's model is doing now. It peaked at the back edge of the rupture. It falls off faster than her model from the simulations. We need to check whether it's falling off too fast or not. We like our model because it doesn't have 37 tapers in it, but it does similar kinds of things. So we need to evaluate versus Jennifer's model whether it's behaving properly. And we will be incorporating directivity into the model, and probably we'll be doing the Spudich and Chiou, and I would guess whatever Brian thinks is the favorite model, we'll do that one. We need to examine the class 2 scaling and to analyze the variability reanalyze our variability. Right now we see, in terms of the variability at magnitudes above 5, we see numbers that are very similar to 2008, but there's certainly greater variability down below 5.
Great. Thank you very much, Bob. Question for Bob and Brian. Everything is clear. Oh, Zia.
Bob, I heard you using 100 hertz in PGA in the same sentence. Is all the developers are the same page?
No. 100 hertz and PGA are, we've used them as the same, but they are in fact a few % different.
So what is going to be the end result in the terms of the final models? Going to be the same or different? Or
for our model, they were the same last time. We haven't decided yet.
Okay.
If we have a lot of data that's from really harder sites, then they won't be the same.
For our model, previously we had 100 hertz. Now we switched to actual PGA values.
Okay. Except our model.
Just a second.
Yeah, we've always used 2 separate regressions for 0.01 and for PGA, so that didn't apply to us.
Yeah.
All right. Any other questions for Brian?
Question,
Yeah.
are you guys planning, Norm and you, to uniformize your Z1.0 parameter as a function of VS30? You have different equations to arrive to.
Oh.
No.
Yeah.
Okay.
Christine, do you have any questions online? Any other? No. Thank you very much. Great.